Hello, everybody. Just to let you know, we will start in about 3 to 4 minutes. All right, it's 1:10. Let's go ahead. Let me start with something. Apologies. Good. I believe you can see lots of screenshots at the moment. Good. And here we go. So before we start with the actual content, let me wait. I have to press the record button. This way we have it all recorded. All right, so from now on everything gets recorded. Fantastic. Good. So you should be seeing my browser right now. You don't see anything else at the moment. The discussions. Thanks so much for participating in the discussions. You might have seen that some of you are still looking for group members. Most recently, Matej has been reaching out to you all. So in case you don't have a group member for assignments 2 and assignments 3, check whether you want to see to work with Matej. Or with others. There are others, some on campus, some are remote. Please keep this in mind when reaching out. On the other hand, to me, it doesn't really matter. I'm actually, you're most welcome to work in hybrid teams, right? So some maybe in Adelaide, some maybe in remote. This definitely works. Just saying that for some teams might actually prefer to meet in person. Some can actually do this overseas. So others can just meet you locally in Adelaide, of course. There are also some technical questions. I have not been able to help Vinci. There was an article regarding a Docker problem also. In case you happen to know of this or how to resolve this, please go ahead and respond. Vinci will for sure appreciate this. There have been other discussions here. For example, what's the textbook of the course? Some of you might have seen there is no textbook in this course. There's also been a long post here by someone. Sorry, someone. I have not been able to respond to it. I will respond to it today, and then there'll be something for everybody to see, of course. So there will be a response later today. Cool. Good. Before we go ahead, let's dive into the actual content of today. Let's start with another tiny survey. We've seen this before last week. Please do this now once more. Do me the favor and indicate whether you've started with your individual assignment number 1. So please visit onlineclicker.org, use poll number 8001, and click on 1 if you have started, click on 2 if you have not started. Do not set up an account. It is not possible to set up an account. Let me just quickly check. I think this is still here. Just double check. Yes, so we'll see. 1,000, some of you have already clicked on it. Okay, good. So this looks much better than last time. Now it's decreasing again a little bit. It's showing you that the 8,000 from last week was still there. Open. Yeah, see that this was last week's result. This is this week's result. I'm really happy to see this inversion here. Thanks so much. Perfectly inversion now. Good. Thanks so much for doing this. This is important, right? You have a few more weeks to go, or not that many. Week 1 was last week. Now we're in week 2, and where are we here? Week 4. So you've got 2 weeks to go for assignment 1. Yes, command control, injection testing, we'll cover this next week, but for everything else, you already have enough information to proceed. And if you have high-level questions, go ahead, post them on the forums. I tend to be reasonably good with responding to the questions. Also, next week, just a super brief reminder, please keep in mind that you need to pick your talks and videos, the papers. And let me have a very quick look who has already selected some. So Vinci has selected papers. I'll just quickly scroll through. And again, David, Yoni, someone, Yeah, good. So we see a couple in here. How many do we have in total? So 11. I believe the course has more than 11. Oh, more than 5 students in this case. So somebody apparently did not pick a second paper just yet. Please do that as soon as possible. Right? Not that somebody else picks it first and then we miss out. For example, if someone has decided to go with for multi-objective integer programming approaches to a feature selection problem. Well, this is simply no table, so don't pick this paper. Okay. All right, this was the admin part. Let's come to the content. And as always, this is now for the broadcaster, so we've done this already. We have one more quick look. What do the statistics say? 81 of you, or 82% have begun with assignment 2, so the other 18%, please start so as soon as possible, meaning after this lecture, please. And as always, I will keep an eye on the chat. So if you have questions along the way, I'll try to answer them when I see them in this lecture. Alrighty, we're ready to go. Quick recap from last week. So we assume that, we've talked a little bit about the motivation of switch-based software engineering. We've seen, hopefully, that approaching a software engineering problem with an optimization or an optimization angle is actually relatively straightforward. Often when we are looking for a design, the representation of the design of a solution is the natural consequence of the raw data. For example, if you're looking at test cases and how test cases should be arranged so that once we process them one by one, we find bugs as quickly as possible. Okay, we simply have the sequence of numbers, so permutation of numbers that we're looking at. If we're evolving source code, because we are trying to make it faster, for example, as we'll see in 2 weeks' time, faster, better, less energy hungry, and so on, we can work directly on the source code itself. So a tree, an abstract tree also, will give us the representation that we can work on right away. Together with the representation, we of course also need some way of assessing how good an approach is. And one way of getting these, we tend to call them fitness functions, objective functions, is that we simply consider the metrics or properties that we are trying to optimize. Right? For example, if we are interested in maximizing branch coverage or line coverage, if we know how to measure branch coverage when doing software testing, we immediately have some function there, some fitness function that can tell us, okay, we're covering 63% or 99% of the code. So yeah, that's a very easy way then of assessing how good a solution is, whether it's a set of test cases, whether it's source code that you're running, or you're not running source code, you're compiling it first sometimes and then executing it. But you get the idea. So one component that we feed into our very general purpose search algorithm is a representation of a solution and a fitness function. Last week, we've also briefly seen, I believe, 4 different, very simple, most of them were very simple, search algorithms themselves. And they were all super generic. For example, it doesn't matter whether we are solving the egg queens problem or the test case prioritization problem, or whether we are, or to some extent, whether we are optimizing source code. We can use a random search, we can use and other approaches as well. But I'll super quickly jump in here. Kate has a question about an example of a representation. Well, just super briefly for you, the test case prioritization from last week, where we say we execute test case 6 first, then number 3, then number 1, number 4, number 2, number 5. If these are as a permutation of 6 numbers. But a representation now would be, we can represent our sequence of 6 test cases simply as a permutation of the 6 numbers. So we do not have to hold on to the individual source code files or the unit tests in maybe Java, but we can just, on a more abstract level, talk about number 1, 2, 3, 4, and 5, and depending on what kind of permutation we create based on these 6, we can use this as an encoding of our solution. But that was just one very quick example. Oops, by the way, if you would like to know more about this, just ask this question. If it's maybe a bit more that you would like to know, ask on the forums, and I'm happy to then elaborate a bit more. But small questions, I'll try really hard to take here during the lecture as well. Good. Okay, so general purpose search algorithms. I've told you last week that there are many different approaches out there. But so in this course here, we essentially just need 4 different ones. First one is random search, because it is almost always possible to randomly generate solutions for your problem that you have. Sorry. And this is where I briefly have to jump in, interrupt myself and say, for me, solution is not necessarily the optimal solution. It's just a solution. It doesn't say that, so the word term solution does not indicate whether we are really looking at the best solution that is actually possible, given the problem that we are trying to solve. So having said this, it's almost always possible to generate solutions at random for a particular problem that you have. For example, we can generate random permutations for the test case prioritization problem. An algorithm that takes this idea on and tries to improve over it is a local search or a hill climber. What we do there is that the first solution gets generated at random, or maybe we have one solution provided by a customer to us, and then we make small changes to the solution. If the new solution is better, we accept it. If it's worse, we discard it and try to generate another solution based on a small variation. So between random search and local search, you don't really need that much more code. In pseudocodes, it's maybe 2 or 3 lines that you need. So in your Java or Python code, it's maybe another 3 lines as well, or 4 lines. And then very quickly, you're not searching randomly through the space anymore, but you can run into a local optimum. And the local optimum is great because you know that once you are stuck in this solution, you can't make any improvements around it, and you can investigate this. You can try to understand something about a problem once you're stuck in the local optimum. With your random search, you're jumping wildly all over the place, and you don't really know whether you could maybe very much improve one solution by just searching locally. So you have the exploration of the space, but also the exploitation that you try to fine-tune at the same time. And here with local search, that's typically fine-tuning. Whereas the random search aspect is the exploration, the jumping around, that will potentially let you find a really good solution, although it might sit far away. Good. Now, with local search, I briefly mentioned it. You don't have a guarantee to find the optimal solution. So depending on where you start, you run into one local optimum. If you start somewhere else, you might get luckier and find a better solution. The third algorithm that we've seen last week is that of what is called simulated annealing, and that tries to let you go out of a local optimum with a particular probability that depends on the performance difference. So if the quality difference is very big, you have a smaller probability of making this jump. If it's just a very small change, let's say here in this case, maybe 3 millimeters. So this is maybe a relatively small difference. We might have a higher probability, initially at least, of making it out of this local optimum once we are stuck. We are always still, if the solution is better, we're accepting it, but we're also accepting worse if it's not, if it's within reason, and if the system itself, the temperature is also fairly high. So this is where the annealing aspect actually comes into play. We have one parameter here called the system's temperature, and this temperature decreases over time. And as this temperature decreases over time, the probability of accepting a worse solution also decreases. This greatly helps in the later phase, again, with the exploitation, so with the fine-tuning. Because later, once we try to do the fine-tuning, we don't want to walk backwards, over and over again, but we try to walk towards better solutions. Now, I'll leave it with this. both local search and simulated routing, they tend to use just a single solution at a time. What genetic algorithms tend to do is they search with a population of solutions, and these populations, these individuals, they are potentially spread out in the entire search space. This has the nice advantage that, well, they can potentially find different local optima, depending on where they start off. They still do some hill climbing individually, but they also recombine information. Or the crossover, so-called crossover, lets you recombine information, and that is a really helpful component. The hypothesis is that there's maybe some good result or some good piece of information from this solution, and the other one that you can recombine, mix in such a way that it allows you to make a big jump, either out of a local optimum or simply into a better space in between the other two solutions. Again, there is no performance guarantee for this, but in practice, they tend to work really well. Depends a bit. So that was a brief, and I think, well, actually very important 10-minute recap. Because, again, these concepts, and I will probably say this at least once more, the algorithms that we are using here are very simple. And in this course, we focus on the formulation of a problem as an optimization problem. So you always have some algorithms that you can apply, very simple ones. I like simple approaches, initially at least, and then I learn about them. I learn about the problem domain, and then I can customize approaches. But initially, let's keep it very, very general. That's very important. And let's focus on formulating something as an optimization problem. So finding a representation and finding a metric or fitness function. Now, in case you wonder what other optimization problems are out there in the real world, well, in our school, about 10 years ago now, we've had a collaboration with the Australian Institute of Sport on team track cycling. So cyclists going around the track. And we've tried to make them, well, to optimize their racing strategies. There's a big ongoing collaboration with the School of Mechanical Engineering, where we're looking at energy, wave energy converters, and making them financially viable. There are quite a number of projects in the mining space in the direction of scheduling mines, scheduling trucks. So there are hundreds of optimization problems there, with lots and lots of industry support. And it's also possible to do government-supported work here in Australia on search-based software engineering as well. So I've had a 3-year fellowship on software adaptations, and I cracked open phones and measured energy consumptions. So in all these cases, no matter what you're looking at, and we're focusing in this course on software engineering problems, but in all these very different situations, everybody's after decision support. So making decisions, designing systems. And it's typically very important to get to better solutions very quickly. And these better solutions, they might be faster, like the cyclists, they might have reduced wear, they might deliver on time, they might let your phone run maybe 2 hours longer, and so on. So there's always lots of demand for decision support. So it is really about finding solutions. It is about finding solutions in this search space. The trouble is, it never looks like this. It's never just a single variable, decision variable that we are changing from left to right. Sometimes we have constraints, so we have certain aspects that we cannot implement. Maybe they are just too expensive, or it's not mechanically possible to generate certain solutions. And what's even worse is, well, very often we are not looking at just a single variable, but maybe at 2 variables, and then we can have all of weird landscapes. Or maybe we look at 20 variables or 100 variables. And then we can get stuck into lots and lots of local optima very easily. And this is what a lot of research focuses then on getting out of the local optima and reliably hitting, for example, let's assume here the right solutions, really good solutions over and over again. Because very often a company makes a decision not only once, single time, but many, many times. And I will actually talk about this in a moment. So in many cases for us now as, let's say, optimization engineers or SPSE engineers, we are considering black boxes. So we have the problem that we are focusing on, we feed in some numbers or something else, maybe source code, and we get a quality out through the fitness function. Now, you will have seen that, or maybe at least in the context of the local search, we have no performance guarantee. So we run the system once, we get into one local optimum, we run the system a second time, we run maybe into the same local optimum, maybe into a very different one, and we do this 20 times, and sometimes we don't even make it into local optimum before we run out of computation time also. So there's a whole lot of stochasticity involved, and we need to deal with this. This is very important because we don't always have this one fixed trajectory of performance increase over time. Because the landscapes are so difficult, so multimodal, we have so many different local optima potentially. Now, I'm saying here that today's lecture is based on another lecture that we typically hold in our evolutionary implementation course. In that course, we normally do this at the very end of the semester, which is way too late. We need to introduce these things a lot earlier, which is why we now get to see it as the second actual lecture. It is important. It has some really, really critical components. Cool. So what will we, in the next hour and a half or so, cover? Maybe hour and 20 minutes. We have to very carefully design our experiments. So we'll cover some situations there. I'll talk about algorithm design. I'll talk about the choice of test problems, on what can you evaluate your approaches. Because typically, both the customer and maybe also the academia, you want to show that your approach is robust. You can change conditions and it still produces very good solutions. And we talked very briefly about measurements and statistics, and at the end, there will be one slide that is, I would say, incredibly important. We'll come to this. We'll gradually work our way towards this slide. All right, let us start with experimentation. Experimentation is important. Running experiments is important. And experimentation has a goal or several goals. You don't just plug things together and press enter and look at the numbers. You're typically interested in showing that your system operates well under particular conditions, for example, or you want to learn about the domain, or there might be lots and lots of different goals of, essentially wasting electricity. Well, it's not wasting electricity, but it's running the computer, right, using it. There has to be a goal for this. So goals are important. Second one is, quite critically, it typically involves an algorithm that's being run. Well, more accurately, it's not the algorithm that's run, but it's an implementation of an algorithm. Sometimes there are subtle differences between these two. So an algorithm is the concept, the implementation can be in MATLAB, in Java, in Python, whatever language you wish to. And sometimes this has ideally it does not matter what language you're using, but you can, depending on which data structures you're using, for example, which libraries, maybe one direction, one language helps you get to the good solutions faster than another. But some of the algorithmic design decisions are, well, they tend to outweigh whatever, they tend to be the more important ones compared to maybe which programming language you use. When you run the algorithm, you run it on particular problems, on instances, on situations, so many problems as well. When we then run the algorithms on the problems, we tend to measure some data, not only the final results, or definitely the final results, but maybe we also measure something along the way. And then in the end, we evaluate the results. Someone present them in a nice, concise, clear way so that the decision maker can then say, okay, I like this approach. I didn't know this about the problem, and so on. And as part of this evaluation, typically everything needs to be documented. So it's all the design decisions, all the goals have to be documented, the algorithms and the implementation. Where do the problems come from? How has it been run? What data was measured? What was presented? And this all needs to be stored. My philosophy is to store more than necessary, that I think are necessary. Because this way I can go back later and interrogate the data afterwards, the runs. So I can do some postdoc analysis on the actual runs. If you want to learn more about this, so you might think, experimentation, computers have been around for decades. You can't really do any research in this direction anymore. Actually, you can. There is a big community effort. I believe it was about 20 authors or so that have written this one paper together recently, so at the end of last year, showing that we are all interested in optimization and in benchmarking and optimization, and there are lots of things that you can do wrong. And in order for us to be able to help the community, we put this one article together. So if you want to learn a bit more about this, read the community effort paper. All right, but let's make this a little bit more tangible for you, maybe. Let's think of the following situation. So there will be a few slides now that are not particularly software engineering focused. Let's say somebody approaches you and says, okay, we want to optimize Australia's road network. So once you start implementing it, well, not right away, of course, this endeavor might cost billions and billions of Australian dollars. If you spend $100 or $1,000 on compute time, then this doesn't really matter because the overall project is so big. So you can, in principle, run hundreds of computers for half a year if you want to, because this one decision that gets implemented, this needs to be a really good one. And if you can improve it by another 1%, this is probably worth another $1,000 or so in electricity. Moreover, it's not just a one run that you run once, but maybe you run several algorithms several times to see, okay, which different solutions can you find. And the goal, whatever setup you put together, you must be able to produce a very good solution just once. So let's keep this design perspective here in mind for a moment. There's another perspective with very different objectives, essentially. That's the production perspective. Let's say you're working at the Australian Post, somewhere in the logistics department, and every day you need to organize the routes of hundreds and hundreds of delivery trucks. So the routes change every time, so where the trucks go. There are lots of constraints, maybe time windows that you have to satisfy. Every truck can also not load all the parcels at once. The drivers might need breaks during certain times, so there are lots of constraints there that you have to consider, different constraints. You can't run this thing for 6 months anymore, but maybe you have 10 minutes, half an hour every day, 1 minute, maybe a bit more than 1 minute. And you need to produce a really good solution in this limited time. You don't have 6 months anymore to produce almost the optimal solution, but maybe within 1 minute you need to be able to produce a really, really good solution. And we can even push this a little further and say, maybe we have an online setting where a decision needs to be made within a few seconds, so we don't have minutes anymore, so seconds, and then maybe you don't have time anymore for very complex genetic algorithms or evolutionary algorithms, but you have to resort to a simple kind or local search in order just to make some improvement over a starting solution. So the time constraint really affects what you're able to do and what approach you are able to take to solving a particular problem. So There's actually a third perspective that look at the perspective here, and that's the academic one. So in the design perspective, we try to find a good solution once, a very good solution once. In the production perspective, we try to find good solutions quickly. And in the academic perspective, we have something that's a bit orthogonal to these two, and that is in our experimentation, we have to meet scientific standards. So we have to be objective, fair, document everything well. Yeah. We'll see lots of components over the next couple of minutes. And all these different perspectives, they have different implications when you're evaluating your results, when you're designing the experiments in the first place, and also when you're evaluating the results. And it's very important to keep this in mind. Let's start with this first component. So before we can run anything, we need to think of an algorithm. Without an algorithm, we can't implement anything, we can't run anything. And so when we're investigating or when we are putting together our algorithm to solve a problem, we have to first cover the two aspects that we've seen over and over and over again. That is, we have to design or choose a representation, and we need our fitness function or way of evaluating the solution. We definitely need these. Once we have this in place, we need to design a suitable neighborhood operator. So you might remember from last week that we considered, for example, swapping two numbers in a permutation in the sequence. So having, for example, 2, 6 as neighbors, we can swap 2, 6 into 6, 2 in a permutation. Or if we are considering just real vectors, a 3.1 we can maybe change to a 3.2 or a 3.0. So a neighborhood operator lets us create a new solution based on either one solution, which is then called a notation for genetic algorithms, or a crossover operation. You might remember from the test case prioritization last week that we looked at permutations and two parents, and the offspring, the children, they contain some information. So the first three, sorry, I just had five fingers on my hands, not 6. They copied all and contained the first three numbers, the first half of the permutation from each parent, and the rest was copied over in order, which is why this happens to be called in order crossover. In any case, so we need to have these variation operators, these neighborhood operators in place, and we need a few more things. We need to decide how we select parents. This can be at random, that we can run a tournament like last week. There are many more alternatives. And once we have them, and once we've produced offspring, we also need to decide how we select or how we put together our next generation. Because the trouble is otherwise that you have parents, you produce offspring, you produce more offspring, and your population just grows and grows and grows and grows and grows. This has lots of detrimental side effects. We don't want this. It makes the algorithm slow. We get distracted, or the algorithm gets distracted by all the potentially very poor, very bad solutions. So we need to remove some solutions. And there are also some ways for doing this. For example, we simply discard the parents, or we consider the union of both parents and offspring, and then use just a better half, so we sort them based on performance, and then we delete the worst solution simply from this pool. Again, lots and lots of ways are possible. Once we have this, well, then there are still two critical components missing. One is, how do we start our algorithm? And typically, people start at random. Sometimes you might be given a solution from an industry client that you can build upon, but very often you start at random. The advantage with a random solution is it's unbiased. The disadvantage is it's unbiased, meaning that it might take a long time for you to find a good solution first. So once we have this initialization method in place, we need one more thing, and that is a termination of the algorithm. How often do we go round? How much time do we spend? Is it an hour? Is it 10 minutes? Do we run for 1,000 solutions? Do we have to build something? Does the building itself cost us money? So there are different ways of deciding when we should stop. Or we might say, okay, we have found a solution that is 5% better than our competitor. We can stop now. We can define a termination criteria in this way as well. All right. So much of this, I've indicated already some wishful thinking, but it's still possible to do lots of bad research if you're not thoroughly thinking about all the different aspects here. So let me give you a bad example, what you should not be doing, or what I should not be doing. So let's say I invent something that I call, for genetic algorithm, a tricky variation operator. Yeah, that's simply what I call it. It's not a swap to nearest numbers, but I call it tricky variation operator. I can call it whatever I wish. And I showed that it's a good idea. So algorithmically, a nice concept by doing the following. I run a standard genetic algorithm, whatever standard means, but that's a different problem. Just to compare myself against, or my approach against something. I take 10 problems that I could find in the literature, and I run my algorithm on it. And it turns out that in 7 cases I'm better, in 1 I'm equal to the standard one, and in 2 cases I'm worse. I write everything up in the paper, and it gets published, so accepted in the journal, gets published, and now the question is, well, I could be happy with this, of course, but what I might not have documented is, okay, what did I actually learn from this experience? And I might not have learned very much. I have learned that maybe publishing a paper is very easy, or not so easy, I don't know. And, well, it's definitely not good work. Work like this too gets published at bad venues, unfortunately, which is why the community efforts like the one from a few pages ago exist. So we are really trying hard to make our field better. We have this problem with experimentation. We do rely very heavily on it, on showing that approaches are robust, that they work reliably across many different problems, and that the evaluation in the end is sound. And you can do many things wrong. And part of today's lecture is simply to show you what are some things that you can do wrong. And in particular here, we're showing you this is not good research. Don't do this. So in this particular case here, let's assume that the paper has been accepted and published. What the readers did probably not learn are the following 4 points. First, these 10 things that I found in the literature, are they actually relevant to it? Does anyone care about them? The fact that they are in the literature doesn't mean too much, unfortunately. Second one is, well, what am I actually claiming? Am I better everywhere? Or what is setting these 7 good ones where I'm beating the others, the other algorithms, so on? What is setting this one apart from the other 2 functions? Are they maybe just 7 copies of each other? Which can technically, well, it probably did not happen, but it is possible to create problems that look mathematically maybe different. But for the algorithm itself, it's not much of a difference whether you have for example, you have a very flat slope or a very steep slope. For algorithms that operate purely based on, okay, is it better or worse? The slope doesn't matter. You can scale it up and down, it does not matter at all. It's just purely comparison based. So the 7 good ones might actually be copies. So I might actually be better than, or a lot worse overall. So I might have, in fact, have been better in 1 case versus the other 2 bad cases. Maybe they were actually substantially different problems. And even though I have these 10 problems that I've run myself on this tricky GA over, it's still not clear to which extent this can actually be generalized. How about other problems? Does it work then as well? And yeah, nothing's been documented, but the paper got accepted. So overall, this is not good, like that, good bad actually. So let's see, what can we do better? The first one starts pretty much with the problem instances and the problems. There are many ways where we can get this from. We can get them from real data. So the company might have cases for us, or maybe we can mine from repositories, or we find other sources of similar problems that we can use for our purposes. And ideally, these are taken from the real world. Right? So they're very much application oriented for this particular, for example, for the Australian Road Network. The disadvantage of focusing on real data is, even though they are maybe the most relevant to anyone who wants to use the approach later on, is there might only be very few data sets available for you to evaluate your approach on. Maybe there's only the Australian network out there, and maybe the Singaporean network and the New Zealandian network. I could imagine that the three actually look structurally quite different. But if that's all the data that you can evaluate on, because they are all so different, maybe your algorithm also tends to perform very, very differently. So if you, in particular, the following can happen if you don't have access to the Australian network right away, but you're developing on the Singaporean network and on the New Zealandian network. You might make design decisions that don't carry over to the Australian network, and this can be really, really misleading. Or see it the other way around. You can actually overfit, you can fine-tune your system so that it works really, really well on a system that looks like, on a network that looks like the Singaporean network or the New Zealand network, for example. But as soon as you approach a different network, like the Australian network, it might just completely break down because it's not used to either large distances or certain other aspects, like high population density or lots and lots of roads on our coast. The approach might or might not work. This is to be kept in mind. In principle, a very good idea to work with real data. In practice, there are some challenges. What else can we do? Well, we can look at repositories or can look through the literature and see what have other people been using. For machine learning, right at the moment, for many years, it's been very popular to share data sets. So yeah, there are definitely data sets for optimization problems as well. I can give you more and more lots and lots of pointers at other libraries, but that's not the point. So many people have been collecting real-world inspired optimization problems or instances. The advantage here is again that there are lots of advantages. First, there are probably lots of problems, and you have much work that you can work by other researchers that you can compare yourself against. So you have lots of ways of checking whether you're doing well or not. The trouble is, because it's just real world inspired, not real world, maybe you're missing out on a crucial aspect. So you're slowly getting further away from what a potential customer in the future might want. And unfortunately, again, we're slowly hitting the problem of overfitting again. The fact that you focus maybe on, for example, only small networks or only large networks might mean that on the other category, you might not perform very well, or your algorithm might be incredibly slow. So the problem of overfitting is maybe not as acute as with the real world instances, but it's definitely a real problem that one has to keep in mind. Lastly, and let's move even further away from reality. For some problems, there are instance generators. So again, programs that are configurable, and they spit out problems. They're typically configurable, and they let you change, for example, the size or how many test cases you're looking at, or maybe there are certain dependencies or characteristics of the test cases. And that's nice, because this way you can generate lots and lots and lots of instances. challenge here with the problem with the generator is, again, they might again miss crucial aspects because the generator is written by a human, and if the human didn't know about something, he or she could not put it into the generator in the first place. Right? So it might again miss a crucial aspect, and also, again, because a human has written it, a human will have put in some bias. It might be hidden bias, it might be a very well-known bias into the generation. For example, having, so maybe it's has to do with respect to different random number generators. Do you always use a uniform distribution? Do you use a Gaussian distribution? What is the right one? I do not know. Maybe it's a mix, maybe you use a power law distribution, maybe you use a Poisson distribution. There are lots and lots of different distributions, but what is representative of the real world? Sometimes it might be uniformly distributed, sometimes maybe you need a Poisson distribution. But a person had to put this into the generator, and sometimes he or she gets it right, and sometimes not. So let's assume, we'll take a short break in a few minutes. Let's assume we have our instances in place. That's good. We have selected in some way, or generated them in some way. Then we run our algorithm. Well, when we run the algorithm, we have to be a little bit careful. As you, well, I was trying to motivate a few times, for example, with the local search, different starting points can result in different final solution quality, but also because we're trying out neighbors at random, so we are never getting the same sequence of our state space exploration. As a consequence, we can never draw any conclusions from a single run. Super important. Should be 10 runs, 30 runs, 100 runs. And this is then unfortunately where my research area gets sometimes a little computationally intensive. So we do need, because we need to reason that over average performance essentially, for our academic perspective at a problem, we do need these multiple runs. For these multiple runs, we measure certain things, we express certain aspects. Something very easy to express is, for example, the average, or mean, or the median. We can easily determine this as the outcome of 5 runs, and then I can report the mean to you or median to you. We can characterize the distribution of the performance using, for example, the standard deviation. If you want to push it a little bit further, we can employ a statistical test to assess to which extent the, or to assess how reliable our conclusions are. We have some examples too. So experimentation is very much about comparison, and we are really, really interested in fair comparisons. We want to use the same hardware that we are running it on, if possible. Same programming language, is probably not as important, because we tend to assume that everybody has already tried to implement an algorithm as efficiently as possible. So that's what we're talking about the implementation side. Using the same hardware is important, and for this it's also important to share the code in the first place. Maybe my code from 10 years ago, technically it runs just as well as code from today, but if I compare my runtime, so what I've been able to achieve in 4 hours 10 years ago versus what I can achieve in 4 hours nowadays, it's probably nowadays my code looks a lot faster. But it's an unfair comparison because I'm now looking at all clock time. So this means that the same resources, or should show you that the same resources should be available to each competitor, essentially, to every party that participates in the experimentation. And maybe lastly here for this slide, it is important that we consider different competition limits or time limits. Why is that important? We might have, maybe this on this picture on the right side should show you, we have time passing from left to right, in particular it's the number of generations that some algorithm performs. And And initially you can see that the green one is better, so let's assume that higher is better. The green one is initially better than the blue one, but then here from about 300 or so, 200 generations on, the blue one suddenly starts to be better. So this is a kind of our algorithm, and it tends, so as time progresses, as we do more and more iterations, our algorithm keeps just getting or finding better and better solutions. But if we don't have that much time, but only 200 generations, then we might want to consider the green algorithm instead of the blue algorithm. By the way, the little dashes here, they are supposed to indicate one standard deviation. So one standard deviation plus, one standard deviation minus. So this might be the result actually of, let's say, 30 independent runs. That is an average and plotted here, which I'm not showing you 30 plus 30, so 60 lines, but only 2 lines plus the whiskers, these little up and down lines, to indicate how wide the distribution actually is at each point in time. All right, so we are measuring things, we're running our algorithms, but what are we actually measuring? There are many, many things that we can measure and what we can also report in the end. What we can report in the end are, as I already mentioned, is, for example, the mean or the median. By the way, this thing here on the right is called a box plot. Some of you have seen this before. It shows here in the box first, for example, the first quarter and the third quarter, the median in the middle. Now we have an idea, okay, where do we see most of our experiments, our data? And these lines here then go up to the minimum and maximum. So we have what's the range of our 30 runs, and where do we expect to see the most, what's the interval of most of our, I think it must be 15 runs now. Where are the 15 runs, where do they tend to be centered around? These box plots unfortunately do not directly show where the individual points ended up. So there might be some here at 1.0, some at 5.0, and in particular, if we have a very discrete space, we might be finding maybe 5, 5, 5, 5, 5 over and over again, and then 10, 10, 10, 10, 10, 10, 10, 10, 10 several times. But maybe there is no solution of 9 or 8, quality 8 also. Yeah, in such a case, a violin plot can help. A violin plot can help greatly because it tries to visualize the density, where did we find all the solutions. In particular here, what this plot is supposed to show you is that around the median, we actually did not have very many solutions. So we found the median sometimes, but there was a bigger block or higher probability of finding solutions, but this is not the same. We're of maybe quality 0.1 and 0.2, but 0.15 was hardly ever found. So the width of the distribution here tries to indicate how often do we find something with a particular value. So we can measure lots and lots of things. I'll show you in lots of different ways as well. So we do not have to resort just to simple measures like what's the mean quality, how many results have we been able to find that are within maybe 10% of the target value and so on. So we can do much, much more. We can help somebody really understand what is the distribution of the results. Good. Now I've briefly indicated this already. What is the budget that we give to each competitor? How do we measure time? What goes onto the x-axis typically? And different scenarios require different approaches. Sometimes we do have to look at CPU time at work clock time. Unfortunately, this is then a bit affected by, okay, how good is the programmer, well, assuming that we have the same CPUs everywhere, but how good is the programmer, what are the libraries that we're using, and so on. What my field tends to do instead is, almost always, is that we look at the number of solutions that we investigated. As an optimizer, I focus on exploration of spaces. And for me, it's important to see how far do I get with, let's say, 10,000 samples. If I get with 10,000 samples to really, really good solutions, that's better than randomly putting 10,000 solutions up into the space and hoping for the best. The number of iterations is what we tend to do. Number of generations, you can rarely, sometimes see this, but not very often nowadays, because it's just unfair. There are some algorithms that employ very, very large population sizes, let's say 1,000, so they always have 1,000 individuals in the population. And of course, in one generation, from one to the next, to the next, to the next, they can potentially test a lot more solutions, but it would just take much more computation time compared to an algorithm that just uses as local search, for example, just a single solution. So you have one solution versus 1,000 in your population. With the one, you can run into local optimum very quickly. But with the factor 1,000, you can find more good solutions, but it also takes a factor 1,000 longer. Well, I'm a bit hand wavy here. Anyhow, you have to be careful. Don't choose very, very large population sizes. What people tend to use are maybe 1, 10, 100. These are good magic numbers if you want to pick some. All right, so we're almost at the break, 3 more slides. So what do we measure, or what are people later on interested in? I've already said it a few times. Often people are, even though we are looking at maybe the number of solutions that we investigated in the space, we're still interested in CPU time. This is important because sometimes you can outsource part of your problem to a really good solver that goes away for 3 hours, comes back with the very best solution, but every time you invoke this, it takes 3 hours. So this is kind of unfair. That's unfair to the other approaches that don't get these 3 hours of outsourced computation time. So efficiency is important. Effectivity is important because you want to get, for example, to the optimal solution or to really good solutions over and over again. So these things tend to be aspects that we measure at the very end, that we record. Sometimes it's interesting to record statistics along the way as well. Like what is and with this, I mean, we don't necessarily focus on the quality directly, but maybe we are trying to capture other aspects. For example, in a genetic algorithm, maybe we want to measure using linear standard deviation in the simplest case. What is the distribution of the population? Did it collapse in the decision space, in the coding space? Is the quality all the same? Are they very spread out? Or are the vectors very different? Are the vectors all the same? This might be very interesting for information for us to debug as well. So sorry, that was here. So vector space, are the qualities all the same? Or are the vectors all the same? So it might be an interesting piece of information to investigate later. There are lots of other things that we can potentially record along the way. Good. What can we maybe report in a table? Well, we can report the number of generated points in the search space, for example. We can report on the number of checks, the samples that it took us to find a particular solution. We can report on the hitting rate, on success rate, so how often have we found the optimal solution, what was the best fitness at the end, and so on. For considering all of this, we can actually have 2 different kinds of algorithms. So we have algorithms that tend to find really good approximation very often. So we don't find the optimal solutions very often, but we have a very high fitness at the end. So good quality solutions very often. This is what we are typically aiming for. The alternatives are maybe algorithms, and we don't see them too often these days, are algorithms that find the optimal solution very quickly, or often, let me put it this way, they find the optimal solution, but if they don't find the optimal solution, maybe because they got distracted by a particular feature of the problem, they might have an extremely low fitness. Maybe they're because of overfitting, right? This could have been an explanation. We overfit it to such an extent that sometimes, depending on the problem that we're looking at, the instance, we find the very best solution very quickly, and in other cases, we are just completely lost. One last thing, and I'm just repeating myself here on purpose. Be fair. Use the same computational limits for each comparator. That is really important. When you do this later on, don't just cite numbers from a paper that you've seen. Okay, you do some research later on. But try to get your hands on the code, run the code, be fair, give everybody the same runtime. And also when you report on results, be aware that some algorithms might, well, maybe use some subsolvers to solve some problems, to put in a lot of computation time in order to make a really, really good solution, so that or do good guess as to in which direction one should go in order to find a good solution. Yeah. Yes. So be fair, that's really important. Good. I think this time, as I've been standing and talking for quite a while now, let's take a quick 5-minute break so everybody can briefly stand up, or I'll briefly sit down and stretch myself a little bit. There are a few things to distract you for 5 minutes. I'll just start the genetic cars just to show you something in the browser. What's happening here is, well, this is not a search-based software engineering problem, but another optimization problem. You've got cars, they are evolving from generation to generation. They are initially very, very random. They have particular designs with a number of wheels and so on, and they get evaluated based on the number of, well, the amount of meters here that they manage to drive in a particular time. And this one seems to have been very lucky now. So we have a good car right away. And now it's being stuck. I'll just leave this, or let this run for maybe 3 or 4 minutes. Let's continue at 2:16. 2:16. So short break for everybody. I'll briefly type this into the chat as well. 2:16, we continue. I have to admit that the cars, we've gotten very lucky with the design, so that we're making quite good progress. Let me just, for fun, briefly restart this car race. Oops. We're now starting from scratch again, so let's see. Maybe we'll see some more interesting design now. Okay, this one seems to be a bit front heavy. Let's see when it gets stuck. Oh, I think you're actually getting very lucky today with your the random number generator. Ooh, front flip. And it's stuck. Let me try this once more. It appears that maybe I can reduce. Oh, I can't. Yeah, I think this is a good start. Good start in the sense that for optimization there should now be a lot of room here for improvement, because all the solutions actually doing really poorly. I think there's a time limit. And it will stop soon. So at the moment, even though this is the best performing car, you might agree with me that it's actually not fantastic. Let's see. This car is also not doing too well. Let's see, what does the next generation look like? Yeah. Okay. Kind of interesting, but okay. Series design for here. Let's see. Next generation. We have some. Yeah, that could be a good one. Let's see. Oh, how many generations were these now? 4 or 5 generations? Or 4 generations? Let's see. We'll have a look at one more. Okay, this one looks like maybe it was a mutation, a variation of one of the previous really good cars. Maybe it was the same. I think it was no blue here, maybe with a slightly smaller spike at the front. Oh, that looks good. So apparently this one must have been the offspring also, or any generated one. Basically. No, it must have been the offspring. So parent, or maybe there was a mutation of the parent. So here on the left, we could just briefly see the previous generation's best. This one here seems to be doing really well. Oops. Yeah, you're welcome to play around with this a bit more. So, okay, here, well, clearance was not enough. Alright, okay, this is good. Cool. So feel free to play around with these things a bit more. I could not find anything in the search by software range space just yet, but on the assignments 2 and 3, we'll give you the opportunity to get in and study with search by software range problems, although they don't run in the browser. These are just visualizations of evolution of local searches that you can run in the browser. So we've got a game of life, we've got some walking robots, and I think these are agents. In the last 2 agents that are seeking food or searching for food. Lots and lots of visualizations out there. Let me. Yeah, I don't have to set up a poll for this. So no online clicker now. No online clicker. Maybe you can just type in the chat. An answer to the floor. We have 2 algorithms that we've been running. The blue one. Let's say we've run each algorithm 100 times, so we have, this is our distribution. The blue one sometimes has achieved a quality of below 50. So 8 runs of quality is equal to 51 to 60. 11 runs ended up getting 71 to 80, and so on. You get the idea. But you've got a spread of your performance. For the sake of this comparison, let us assume that both the mean and the median of both the red distribution and the blue distribution are identical. Now I'm asking you, which algorithm do you prefer? So don't be shy, use the chat. I'm not sure whether you can actually see my chat window now. I think you can't. So type in the chat. So to everybody, do you think the blue algorithm is better? Do you think the red algorithm is better? Well, when would you pick one algorithm over the other one? I'll just let you think about this for a few seconds. Actually, let me do the following. Sorry. You can use my technology. I had forgotten about this. I will very briefly, this maybe gives you the opportunity to discuss a bit more, put you into rooms, and I'll get you back soon. You will get a notification that you have 1 minute to wrap everything up. Just feel free to keep discussing until then. Let's do this 2-minute exercise. So I'll briefly put you all in rooms, and then you have an opportunity there to discuss briefly. So which one is algorithm, which one is better, why, and why? Blue versus red.
Um, which algorithm do you think is better?
Um, Actually, I think maybe the Boo algorithm.
I agree with you, but I think we need more information because we just have like this,
Yeah, just
Um,
have the graph. So I think
it's
they provide some fit-led information
yeah,
because
like
they use the because I think they use the fit-led information to form the fit-led
oh,
function to uh guide that algorithm, right?
yeah. So yeah, I think but from the like picture, it looks like algorithm B, the blue one is having like consistent, results. But I think we need to do some sort of testing.
Yes, maybe maybe they show some raw data will much better. So I have to know what's going on.
Yes,
Yeah,
we don't know like much information about what kind of data set they're using, things like that.
yeah,
So
yeah.
yep,
Maybe the this is the customer list or customer requirements, right? So maybe the customer maybe list some uh how to say that I'm not sure. Yeah,
yep, it makes sense. Like there might be some objectives that we don't know about.
yeah,
So
yeah, absolutely.
yep, yep. Thank you. It's a
Okay,
good discussion.
okay. Thank you. See you.
All right, we have to wait another 16 seconds. All right, now everybody's getting pulled back automatically into the main classroom. Good, good, good. I don't know. Who wants to go? Which group thinks blue is better? Which group thinks red is better? Just share with me.
I think the blue is better one because we need a stable algorithm.
Stable, but it has a broader distribution.
That is distribution.
Yes. Okay, my bad.
Okay.
Yes, yes.
I pick red one. Thank you.
No, no, red one. Okay, good. No problem. Okay, what are other opinions? I'm not saying anything about this. What are other opinions?
I feel like we need to know about the objectives and we need additional information to base our judgment.
So, Sayone, what would help you? What kind of information do you need? Sayone, you muted, just to let you know.
Yeah, I'm thinking
Yeah,
basically more information about the fitness. I'm really not sure.
yeah, because I think that we SBSE is use the fitless information to form the predictive or modeling, right? So this according to this graph seem to be the algorithm A, the red bar is the bad algorithm, but maybe a local optimization.
No, it depends. I'm just collecting opinions right now or thoughts. Okay, what else do we have? So we've heard it from, sorry, I can't remember who the first one was, but then was Sayoni and someone. Who else wants to say something very briefly? Blue or red or why or anyone? Really, I think you're not muted, so maybe you want to say something. Um, so what was it? All right, the first one so maybe a red one is the best one. So what this is showing you is that in 25 runs, of maybe in total 50 runs in this case, the red algorithm has achieved a fitness, a quality of 71 to 80. The other one just 11 times. Overall mean and median performance is just, for the sake of this comparison, supposed to be the same, identical. But let's assume that we're actually maximizing. So one algorithm, so the red one, has never found a really, really good solution, and the other one has found it maybe 5 times. But has also found worse solutions in a number of times. So worst solutions, worst performance 3 times. And maybe we're going here, just a hunch, Kate says algorithm 1. It's we have A and B here. I do not know which one is better. I think I'm going to side with Psionic, that we need more information. I do not know. I have not given this to you on purpose. We do not know what might actually be acceptable. Right? Keep in mind the 2 motivating examples from about an hour ago now. The design system, also the design case, where we're optimizing the road network, and maybe we're trying to find a really, really good solution just once. In this case, I would very much prefer the blue algorithm, because it doesn't matter. We can run it 50 times, we can run it another 50 times. We have a small chance of actually finding really good solutions here on the right-hand side, assuming that 91 and 100 actually stands for best solutions. Right? Whereas the red one has a nice, well, we have a nice tight confidence interval, or we see the solutions in the same band over and over again. But we don't deviate from this very much. So we have maybe good approximations here, or decent qualities reliably over and over again, but not really good solutions. So I think there's no single answer here for this. Maybe B is good for design problems, A is good for production problems. It depends, right? So very important. There was no correct answer to this. There was also no wrong answer to this. So assuming that really mean and median are the performance are the same. One standard deviation in the red case is probably smaller, but then with a wider standard deviation here in the blue case, you also get better solutions. You also get worse solutions, but it depends on what you're after. Right? So objectives to some extent are really important. And what someone was saying regarding maybe local optimization or local optima, potentially maybe there are some solutions or something. This here might tell us about maybe the problem itself, and together with some component that algorithm A has that B doesn't have. So A might prefer, maybe it's even 25 times the very same solution, right? We don't see this yet. Or it might be 25 times different solutions that all have these similar performances, right? We are not learning this aspect. So there's definitely a lot of information not presented here. We could dig a lot deeper. Good. So thanks a lot for participating. I'm starting to like these breakout groups. Don't worry, we will not run them too often. Good. Now, I've talked many times about different algorithms. Well, the algorithms themselves, as you're running them, we've seen this a few minutes ago already, just before the break, they can behave differently. Sometimes one algorithm looks a lot better than another one, but just based on the time limit. Let's here again assume that time passes from left to right. So that's my implicit assumption, simply all the time that time passes from left to right. And this is on the y-axis, the performance. And also, of course, let's assume that we are maximizing here. So we have 2 different algorithms, blue and red, over time. And we see here again, blue has some standard deviation here indicated, and red one is a deterministic algorithm. Think of it in the sense of maybe bubble sort or something along these lines, so something that makes no really any, or that has very little room for decisions. So very, very fixed quality improvements, no alternatives. Again, what do you think here? I'm not going to split you into different groups here right now. What do you think? Which algorithm is which algorithm is better? The blue one or the red one? I'll let you think about this. As soon as you have something, just shout it out, or speak it out, don't shout, or type it in the chat. I'll give you 30 seconds or so. Which algorithm do you think is better, blue or red? Zhonghao has already written a very good question in the chat. I'll leave this unanswered for the moment. I'll just give everybody maybe another 30 seconds to think about this. Which algorithm is better, why, and when? Another 10 seconds. Before anyone else says something, let me jump into Zhonghao's question. That's my last. Yes, potentially we should have tried to let both algorithms run longer, because there's a good chance, based on the slope, that B would have overtaken A very, very soon. But we stopped early, right? Bad luck. These are the numbers that we have. So potentially, B would have overtaken it, but you never know. There's no guarantee. We don't have it recorded. We don't know. All right. What do others think? Is A better? Is B better? Any volunteers? Any thoughts? What did we put the following? Wait, do you maybe hear about this beginning? What do you see? B is deterministic. A has enormous performance variation here. This can also mean that maybe for short run times, B is actually better. Actually, at the very least, we have a performance guarantee. In the other case, we might have some, I don't know, 5% of the runs, 10% of the runs might actually still be worse than B. And if it's really critical for us to have a performance guarantee, then we might, for short run times, still stick to B. Maybe from here on, plus minus 1 standard deviation. This gives us in total 75% of the runs, so the variance is not that high anymore. So we are not that likely to be actually worse than B, and at the end, there's pretty much no performance variance anymore at all. No more comments in the tech chat? No, not yet. So it's much like in the situation from one slide before. It depends what we're after. It depends on what we're after, and in particular here, the runtime was a bit of an issue. We should not have stopped this early. But keep this in mind. If you're just looking at the very end, on the far right, okay, well, I'm blocking this now, but you can't see that I'm blocking it. If you're just measuring the performance at the end, you do not know what the trajectory is. You have no way of seeing this. Good, let's look at this a little bit more. So trajectories over time. This can actually, well, depending on what kind of algorithm you have, so as time passes, the quality, or let's say this is maybe simulated annealing, it might actually go up and down, up and down. Can happen. And in particular towards the end, it might accidentally go down again, because as you might remember, in simulated annealing, you can actually accept worse solutions. So this is a single run, then we do a second run, and it might be completely different. It will be kind of completely different, as it bumps differently, the starting direction is different one. We're working with randomized algorithms, so we do have to expect something, so that something like this happens. Ideally, of course, performance always goes just up. On average, it goes up, but we don't know it. We don't have, it's not guaranteed. So here on average, performance goes up, but small local effects, local phases, we might be missing out on a lot of information. This one should be 2 millimeters higher, but we get the point, right? Average is not very accurate. So by presenting only the average, we are cutting off a lot of potentially very interesting information for us as optimizers. And well, what's the alternative? We can of course just show 50 different runs on top of each other, but this also means that we end up with these pictures where we can't really see anything anymore. So that's a little tricky to understand what is actually being shown there. Although what the average performance was. If I squint really hard, I can see a bit of a band, but I might be missing out on, for example, these effects here where there's the kind of the majority of the runs is going down here, but 2 runs were up here. Maybe there's something either about the landscape, this shape, the surface that I can learn about the problem, or maybe it was just by luck. We can move a little bit further, so not just show the average, for example, but we can show confidence intervals. So showing how many runs would be within, for example, or which interval covers 95% of the distribution. This is now, what you can see here, not an optimization run. It is some simulation, relatively current, with some COVID-19 modeling that I've just showed earlier today. With some aspect of, or some percentage of the population having been infected, and this might, depending on our simulations or so, what we do in the computer, it might increase quickly very early or later, and you can see some very faint lines here. So these are quite widespread between the different curves here. So we're not maximizing the number of infected people here, by no means, definitely not. I hope everybody gets sick, gets well very soon and gets vaccinated very soon. What we can do here with all these 1,000 runs here that we recorded is we can show as a shaded area the area that would cover 95% of experiments. There are packages that let you do this, and the nice thing is that something like this is much more easily interpretable, for example, with the median and the cloud around it, than, for example, a messy picture like this one. Or a chalk picture here where you just have the median line or the average line. So, yeah, oops, sorry, jumped one too far. So there are packages nowadays that let you to achieve such visualizations. No problem at all. In R, in Python, in MATLAB. Okay, since I mentioned confidence intervals, it's not very far to get from there to statistical comparisons in general and statistical tests. They are important because they try to capture how different distributions are. And this is important for us because very often we have, as you've seen many times now today, and maybe a little bit also last week, we have this luck involved sometimes. Some ones get lucky and they very quickly make a lot of progress, and others don't get that lucky. And we want to be sure that we make reliable statements about our approach. So that later we can say that, for example, the newbie recommendation or lucky recombination is actually better than, for example, uniform crossover or the in order crossover from the test case prioritizations that you've seen last week. Statistical tests are important for the following reasons. Let's briefly investigate the following situation. So we have here our algorithm, let's say 30 runs. I'll show how many these are. Let's say these are 30 runs. We run the 30, or so we do the 30 runs once. And it gives us maybe something like a distribution of this. It's highly simplified, but it should give you an idea that we see some performance here a bit often, and some really good ones not so often, and some really bad ones not so often. So just an illustration. Now we run the very same algorithm again. Right? Nothing has changed. Just maybe 5 minutes later, we run the same algorithm again 30 times, and ever so slightly, the performance is a bit different, right? Because it's a randomized algorithm. We make different random decisions at times, and it happens to be that the 30 runs now actually happen to be a little bit lower. So we have on average slightly lower performance. The mean is a bit lower, the maximum and minimum is also a bit lower. And now another 10 minutes later, maybe I run it again, and it's again lower. So what happened? Okay, well, let's say these were 10 runs, so not 30 runs each time. Are they actually from the same algorithm? Well, yes, we know it's from the same algorithm. So what do we learn here? They're all from to some extent, they're all samples from the actual distribution, but they were grouped differently. They were not good. So we just had different amounts of luck with our 10 samples because we're talking about just 10 samples. With more samples, we would not have seen this. It's very unlikely. So, but this is something that you have to be aware of. You run your algorithm to take 10 times, you get one distribution, you run it tomorrow, you get a different distribution, you can run it again, or maybe on the weekend, you get again 10 different numbers out of it. Now with 10 runs, this can happen, in my experience, that you have slight differences and maybe major differences. If this would actually be representing not 3 times 10 runs, but 3 times 1 million runs, they are probably not from the same distribution anymore. So maybe something else has changed. Maybe you have changed the code. Maybe there's a bug that was now introduced. Maybe, maybe you changed the random number generator. There was a major change here suddenly because the means are changed and it looks like they are now not within one standard deviation anymore. But also still keep this in mind. You run your algorithm 1 million times today, 1 million times tomorrow, and the mean will ever so slightly be different on the average, as a mean and median, ever so slightly. Even if it's the very same implementation. Now, in order to say that there is actually, or to determine whether there is a difference between the 2 distributions, or 3 distributions here, some statistical tests can help. There are lots of statistical tests out there, and I'll point you at some additional resources in a moment. What you have to be aware of is that different tests make different assumptions. So, for example, there's one enter in many. Sorry. The t-test assumes that you have normal distributed data. But typically with optimization ones, you don't have this because you're hitting a maximum. You're hitting a maximum or you're staying below the maximum, so it's not a nicely normal distributed, but it's a bit skewed. So you have really good solutions very often, but not. It's normally not. It's typically not normal distributed. An alternative that one is I tend to prefer over the t-test is, for example, the rank sum test, so Wilcoxon rank sum test. They just rank the solutions and then create a union, unified rank. You take the union of the outcomes of, for example, 2 experiments, you rank them, and then you count ranks and add them up and do some small calculation and calculate the average rank over it and the variation as well. And based on this, then you determine whether the 2 distributions that these samples come from are different or not with a particular confidence. You do not need to know much more than this, but you do not need to know much more than this. But it is important to know or to remember that statistical tests typically make some assumptions. Be aware of the assumptions. That's really important. Look them up if you want to on Wikipedia, or just Google them, or use Baidu or search engines. Textbooks. There's a lot of information out there in the form of video tutorials you can probably also find some Chinese websites like Yoku and Tudo. You don't have to implement these from scratch. I have not asked you to implement these from scratch. What is quite helpful, if I remember correctly, here is steppages.org. It will help you to find the right statistical test, because there's only 24 different ones out there. It's easy to pick the wrong one. I'll briefly go back once. If you're just interested in comparing performances in the end, a good choice is the Wilcoxon rank sum test, because the t-test makes the assumption of normal distribution. Much more information out there. We're not worried about this today. So let me briefly come back to this bad example from, about an hour and 20 ago, right? Let's see whether we can improve upon this poor research that I apparently have been able to publish in this example. Let's assume the following. So I invented my evolutionary algorithm for a particular problem. I looked around, I found 3 other evolutionary algorithms, and maybe even certainly other evolutionary algorithms, and maybe a traditional approach, if you're looking at it, maybe a proper mathematical way of solving the problem. So this would be 4 competitors. And I wanted to see, okay, when is my algorithm better and why is it better? So I went ahead and I used an instance generator that has 2 parameters. One n for the problem size, n is to be used for the number of test cases, for example, number of cities, if you're looking at a traveling salesperson problem. So that's size, how many numbers you have in your vector. And it has some problem-specific indicator that I don't want to talk about because first I didn't write down what it is, but it doesn't really matter. It's something that lets me set maybe the number of local optimals. Choosing just one combination of n and k is, well, we can do a lot better. We can use different combinations. We can use 10 values of k combining with 10 values of n. So this gives us a total of 100 problem instances. Given this 100 problem instances, I run all the algorithms and this traditional heuristic 100 times. And I record the average evaluations to find a solution or success rate or mean best fitness and so on. I can generate lots and lots of tables with this. Yeah. And in the end, I end up putting maybe my code and instances online as well so that other people can reproduce this. So at the moment, it looks like it's researched on a lot better. For the documentation part, for the evaluation part, I can do much more than just presenting numbers in tables. Versus would be it's a 3-dimensional table already, or just one very long one, 2-dimensional one, and that's a really long one with 100 rows. What I can do is to help people understand what is happening here. I can visualize 3-dimensional or 2-dimensional. I can visualize surfaces in 3D, where the 3rd dimension can then be, for example, the average final fitness. And here in this case, let's say this one is n, this one is k. As I vary the 2 parameters, apparently fitness goes down and then goes up again. You see overall a relatively smooth surface. Keep in mind, this is not the problem itself, but this is, so each point here now denotes a particular generated instance with some interpolation, of course. And as I explore this instance space, so not the concrete instance, but as I look over different instances, I have maybe something that that ends up being very difficult for my algorithm, also the other way around. So this is maybe difficult, this is very easy, assuming that we're maximizing here. And there's some valley here as well, but overall it looks relatively smooth because I've run it 100 times. If I would run it just once or 10 times, it would look very choppy and not very nice. So by looking at plots like these, by running statistic tests as well, I can then make statements. I can say, hey, my EA works well in some cases, it's strong in other cases, and it's maybe comparable in some 3rd category. So this way I can answer the when question. When does my approach work? And the nice thing is when I put sentences like this into my paper or report, others can go ahead and consider these and say, all right, my problem seems to have some characteristics that are similar to what Marcus investigated. Marcus said, when this and this happens, then this particular component can help. So let me throw it in. Maybe it helps, maybe not. You want to help your fellow colleagues, so whether it's in academia, whether it's in a team, when you're working maybe for a customer, or maybe you're doing some in-house development. So the when question is important. Why it gets a little trickier to investigate, because maybe the instances are so complex that analyzing why your data is not straightforward. Your algorithm itself, or my algorithm here in this case, might be very complex. So then understanding really the interactions of the landscape together with the algorithmic components might be very, very difficult. But it's desirable. If you can answer the why question as well, then you have at least your paper has a very good chance of getting accepted. And maybe you're also showing to a customer, or your team leader, that hey, you've really understood what the problem is about, and we can in the future make informed decisions. Yes, and we do all this so that we achieve generalizable results, so both on the algorithmic side, or largely on the algorithmic side, and also on the insights side, so that we can later on design the next best, the next better algorithm for a particular problem. Because I said I published my code afterwards, actually I'm furthering future research as well. Others can build upon it, they can benchmark against my results, they can run my code. It will be much easier than if they had to re-implement everything from scratch just based on a short description in the paper. Cool. All right, we've covered a lot of it about experimentation, a lot of the do's and don'ts, where do we get the instances from, how do we analyze the results in the end. I want to briefly show you that this is not state of the art in all fields just yet. Particularly a few years ago, I found this tutorial by Lionel at a software engineering conference. Well, in particular, it was at the Symposium of Search-Based Software Engineering, one of the first SPSE events. Just one of the first pure SPSE events. And so this tutorial, which much like here is essentially a lecture that you give at a conference, so it's very different from presenting your newest research results, but here it's more like educating your fellow researchers, and maybe helping also educating our fellow researchers, but predominantly PhD students, and maybe those who are early in their careers. So here with this tutorial, Lionel wanted to raise some awareness for, things that are happening, especially particularly when it comes to conducting and analyzing empirical studies. If you want to learn more about this, the full tutorial is online. I just want to briefly highlight about 4 or 5 slides from his tutorial because I think it shows that SPSE has changed over the years and largely affected by the optimizers that have come into that field. So Lionel has been, I'll skim over some of the content here. So Lionel has conducted a literature review, checking lots of papers at the top conferences at them. How do they evaluate their experiments as soon as there's some randomized performance in them, some randomized algorithms? So this was still at the very beginning of SPSE. Now the field is more mature and we see more structured, more robust approaches. So back then, the idea was that in search-based software engineering you have a search variant, a random search approach that could define the solution. And they were back then, about 10 years ago, under the impression that you always can have a proper mathematical approach to some problems as well. Nowadays, this is not longer the case. For example, in my work here on energy minimization, we don't have any mathematical formulation, and we will never have one. So there is no approach anymore that is an alternative to search-based or random search approach. But back then, 10 years ago, some problems were more fundamental. There could be proper mathematical approaches. So what Lionel and his colleagues had done, they looked at a particular top journal, top conference, and another SPSE conference across 2 years. They've noticed how many papers had some randomized algorithms in them, so there were about just 7% and 7% in 29. And as you can already see here, apparently there was a major jump, and nowadays it's even more. So more and more people are using randomized algorithms in their papers or in their research because it helps, tends to help. So it was on the upwards trajectory, and along with this upwards trajectory, you can also see some development. So these are the papers that they considered. We see that many people here, although they've had maybe half the people of the research groups, even though they've used a randomized approach, they just did a single repetition. Something that nowadays you could pretty much never get accepted anymore, because you want to show how robust your approach is. It depends a bit on the objectives again, what you're trying to achieve, but a single run could be considered just a lucky run nowadays. But you see some are trying 100 runs. They might be, and then they have maybe reported on mean performance, average performance, but since this is a test here in 2009, you didn't really see any. This has changed for 2010. First, a lot more papers. Second, at least relative terms, more papers used more runs, 50 runs, 100 runs. As I said, these are good magic numbers. 1,000 is maybe overdoing it a bit, but it depends again on what you are trying to solve. And also here you can see more papers use also a broader range, broader spectrum of statistical tests. Nowadays, I know this is from about years ago now, so nowadays the average approach that you can see in an accepted paper at one of these top venues is decent, is good, solid, is good number of runs, good number of different instances if possible, or at least broadly set up. And often, still not always, the code is online for reproducibility or replicability purposes. So with this, so if you want to learn more about this, Lionel has this tutorial online. It's also linked to via the website. Now, just in time, this is the very last slide. There's one summary that I think is really critical, really important for today. I know everything on this slide is red, but believe me, I've done this on purpose. No, you should put everything in red because you can't really tell anymore the unimportant things apart from the important ones. But here, everything is really important. So first, when you run experiments, you organize. Define a goal, decide what you want, and define what you want to measure. Next, choose your test problems very carefully. Be unbiased if possible, unless you can justify a particular bias. Make a proper plan, and try to estimate how long your experiments will actually run. Otherwise, you end up missing the deadline because your experiments will still be running in 2 months' time. So there are very often some trade-offs that one has to achieve. Perform a sufficient number of runs when your algorithm is a randomized one, like with random search, book climbers, genetic algorithms, you know all this. Keep all experimental data, so log files are your friend. Tend to, if needed, do log more than necessary, or have a random number generator somehow where you can provide it with a particular seed so that you can rerun the experiments later and still perfectly rerun them, and record additional information. Because going back and then recording additional information tends to be just very cumbersome, and you have to adjust your tool chains, you have to run for the compute cluster to be available again, and so on. So don't throw anything away. Use good statistics. Even Microsoft Excel has a few things built in. Their standard tools. R is very good. Python has lots of packages, so there's nowadays no excuse for not using any good visualizations and good statistical text segment. Present the results well. I like surfaces. I like parallel coordinate plots. There are many ways of having nice tables that support that help you convey a message very nicely. Don't oversell. So watch the discovery plans. Try really to answer when your algorithm is better and why it's better. And aim at something in general that is generalizable. Very important. You can overfit if that's one problem that you're trying to solve is really difficult and you're the first person to solve it. But in general, at least in my area, we are trying to find something, design a system, design an approach that can reliably work under many conditions or for many different scenarios. Publish your code at the end, unless you're compiling an object to this, of course. Lastly, once more, I'm planning to add this. I think it's a 40 or 50 page paper by now. It's more like a book almost, a thin booklet. At this community effort that I was fortunate to participate in on benchmarking optimization. So if you want to learn more, have a look at this one later today. Good. Right on time. 3 p.m. I'm happy to stay here for maybe another minute. I do have to run to the next meeting, unfortunately. In case you have any questions, just type them into the chat or maybe post a question on the discussions forum later. So officially, that's it for today. I have not forgotten about Zoom 1 here, the long question here. I will respond to it later today. That's all. Thank you. I'll just stay here for another 45 seconds or so, just in case anyone wants to ask any questions. And as always, of course, I will provide the link to the recording later. Well, I'm not seeing any questions at the moment. So, yeah, if you have any, post them on the forum, and feel free to also discuss there. It doesn't have to be just manager one. You can discuss with each other as well. All right, I'll stop the meeting now. Thanks very much, and I'll see you next week.